Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. Okay, it is really my privilege to welcome you to this session, Computational Science Research in Latin America. My name is Jaime Puente. I am responsible for Microsoft Research external engagements in Latin America and the Caribbean. The objective of this session is to give you a snapshot of the kind of computational research that is being conducted in Latin America through the description of a couple of projects, which, despite the fact that they are still in their early stages of execution, they promise to be very successful projects. Originally, we were going to have 3 speakers. Unfortunately, one of them, Professor Carlos Joly from Unicamp in Brazil, canceled his participation at the last minute due to health issues. So we wish Carlos a prompt recovery. With that being said, I would like to introduce the first speaker. The first speaker will be Dr. Ricardo Bencio. Dr. Bencio is an assistant professor at University of São Paulo, São Paulo's Medical School in Ribeirão Preto, in the state of São Paulo, where he teaches biomedical informatics. Dr. Bencio leads the Laboratory for Biological Information Processing at USP, University of São Paulo, where he and his team conduct research on subjects such as cancer, malaria, biorubber, and biofuels. The title of his talk, as you can see there, is Information Technology Applied to Bioenergy Genomics. This talk is related to a project that is being funded by the Microsoft Research FAPESP Institute for ICT Research. This is one of the 2 virtual institutes that Microsoft Research has established in the region, whose goal is to explore the application of computer science to tackle the fundamental research challenges existing in areas such as healthcare, energy production, education, transforming education really, and the various disciplines covered by the environmental sciences. So please join me welcoming Dr. Ricardo Bencio.
Thank you. Thank you.
Okay, thank you, Ricardo.
So, first of all, I would like to thank the organizer for this kind invitation. It's my pleasure to be here. I lived here in the city, well, not in this city, but in Seattle for 2 years, and it's very nice to be back. And so let's start. So the idea here is to, let me start with the goals of this project. So the project is something that we started 4 months ago. It's really in the beginning of we are in the beginning of this research project, and we don't have yet results to show. So it's too early for results, but we are getting there. And I would like to give you an overview of what's going on, what we are going to do. It's more it's kind of an inspirational kind of talk than actually results. Okay, we don't have results yet. I'm going to talk to you about what you plan to do. Okay. So the goal is to develop user-friendly software to rationally guess biological functions of genes from sugarcane. Put it simply like that. So I will explain a little bit more what I meant by that. So, but the idea is to develop user-friendly software to rationally guess the biological functions of genes in the plant sugarcane. Okay, and why we want to do that? So one of the main motivation for this work is that everybody knows that we are facing a tough time in terms of energy production, energy requirements. We have, for several reasons, we have to devise new sources of energy. There's sun, there's nuclear power, which is not so new and controversial, but I support nuclear power. I think it's depending on how you're going to do, it's an important thing. And there's other options, not just the petroleum-based, and for several reasons. Not just because the weather is getting weird, it's not just climate. We are not just getting hotter, but it's getting weird. Everything it's becoming weird, and we believe that this is because of the global warming effect, or the production of too much CO2 in the atmosphere, and because of us. At least I believe in this theory. Let's see what the environmental scientists think about that. But so the other ways to produce and generate energy are important, and biofuels is one of those. Of course, it's an important alternative energy source, but the problem is that you can't just put like biofuels and that's it. There's more on that. There's more. There are some subtle details on this biofuel world. To be a good biofuel, you have to meet some requirements. It's not just be renewable and that's it. For example, this paper that came up in Science last year is really good, and they show clearly that there's lots of options for biofuels, for production of energy from biofuels. But we have to consider some important things. For example, a good biofuel does not compete with food. So this is important. So here in US, the main source of biofuel is the biofuel made from corn. And of course, we eat corn, right? So when you diverge your efforts to produce biofuel from corn, you are competing with food. I'm not saying that this is necessarily bad, because the system can arrange itself. We can figure out how to solve this problem. But since the beginning, you have to know that you're dealing with something that competes with food, and this is an important issue. What else? The crops can be some crops. It can cause land clearing. So, if you in Brazil we had this examples. If you want to plant the crops that are going to provide you biofuels in places that are occupied by other things, for example, cattle, you have to displace this cattle to other places. So it's not an a decent environmental solution to just cut down the forest to plant something that will generate biofuel, of course. So we have to put this into the equation too. But the most important thing, I think, is it has to actually have some advantages in reducing gas emissions, greenhouse gas emissions. Otherwise, you're going to use some biofuel, some solution, some alternative to make things worse. No, that's not what we want, right? So, if you are considering biofuels, you have to put all of these things into the equation. It's a system. It's not so simple as just plant whatever you want to plant and that's it. So this is important. And in Brazil, we think that we have one solution for this problem. The sugarcane has been explored in Brazil since the beginning of our record written story. So as soon as the Portuguese arrived, they already had some skills in sugarcane crops. Of course, not for biofuels, but to produce sugar. And they already had these skills, so we had some close connection to sugarcane from a long time. So sugarcane is something that has been there for a while, and we have been mastering this crop for a long time. This is an important slide to show, because one of the fears that people has when we talk about sugarcane and biofuels is that these guys are going to destroy the whole Amazon forest to plant sugarcane. No, these red spots are where the sugarcane is concentrated. Sugarcane doesn't like the rainforest. Even if we want to damp down, it's impossible because it's not going to be productive. So the main region where we plant sugarcane is in this red dots here. In fact, I live here in the middle of this sugarcane red dot. So it's a really important subject, not only to the country as a whole, but for my region specifically. And we think that the sugarcane crop is one solution that meets the criteria we just, the dilemma I was talking about in the previous slide. So it doesn't compete with food directly, of course. Sugar cane is to make sugar, of course, but the demand for sugar, it's not so high that it can really shift the balance if we decide to use this as an energy crop. So we think that this is an important issue. It's not like corn. People don't use sugar as much as they use corn, and sugar has other possible sources. And that's why we think it's an important crop, and we think that this is one solution for the problem. And since we have an experience with this crop in terms of production energy, the state of São Paulo, is where I live, is the richest state in Brazil, launched a big initiative called BioN. This BioN project is a project to enhance and secure Brazil's leadership in this field, so in the field of bioenergy, but of course not just sugarcane bioenergy, the whole business of biofuels. And they devised this program. It's a big program. It's a research program in Brazil that had several points in the agenda. For example, one of them, the one I'm interested in now, is the biomass production. The production of more stuff, more mass from the sugarcane plant. But there are other topics being studied too. For example, ethanol technologies, the conversion of sugar into ethanol. This is important too, and has nothing to do with the plant itself. Or engines in Brazil, including my own car. Every new car is flex, what we call flex. It works with gas and ethanol, and it's transparent to the user. So you just put ethanol, and ethanol is cheaper. That's why everybody uses ethanol. But if something happens, some climate or some issue happens, you can just put gas, and it's really transparent. And moreover, we can say that in Brazil, the alternative fuel for cars, at least, the alternative fuel is gas, because more than 50% of the cars are powered by biofuel nowadays. Of course, depends on the region. Some places, they have more difficulty to get ethanol. But anyway, to study the engines, the cars powered by bioethanol, it's an important issue too. And finally, and maybe more important than everything else, the social and economical and environmental impacts. So we want to do something really responsible. We don't want to destroy our country and the other countries in the planet, telling everybody to plant sugarcane all over the place. No, that's not the idea. So there's also a division in this program that studies the social impacts, the economic impact. What happens if we actually pass it from, let's say, 10% of ethanol, bioethanol in the gas, mixing in the gas, to 11% or 15%. What happens in terms of economy? So there are some people studying this and working in these things. So, but what I want to focus here is the Biomass Research Division, which is the division that is going to, that proposes the scientific challenge of sequence the whole, or at least a great part of the sugarcane genome. Okay, so you have the overview of the bioenergy endeavor in Brazil, the research endeavor. There's one part which is biomass, and in this part there's one part which is dealing with the sugarcane genomics, which is the part that looks more scientific. So there's the other parts, there's some technological issues, there are innovation issues. This one is more scientific. It's the one we want to do science, but science, useful science. well, anyway. But there's an important problem. Now we got into the biology of the thing. If you have the genes, if you have the sequence, and you don't know the function, it's pretty much useless. To know the function of a gene, you have the sequence, you sequence the genome of your plant. But if you just get the soup of letters, that's not going to let you anywhere. So we have to, one important thing, one important scientific challenge in this whole program is to assign functions to these genes that are going to be sequenced. And for that, we saw an opportunity. Microsoft, as Jaime said, opened a call for grants in Brazil because they were creating this joint virtual institute with FAPESP, which is the most important, I think, the most important grant agency in Brazil. They had this. They set up this virtual institute where they're going to fund several projects. And so they opened this call, and there's this BioN program. And we saw this as an opportunity to merge both programs because they live in separate worlds. So this is really something from FAPESP. This is, the other one is FAPESP Microsoft. We saw this as an opportunity to merge the programs and do some applied, use-inspired research, which is well described by the famous quadrant. And I like this thing because our research, we think that our research, it's like it fits well with the Pasteur quadrant, which is like you have pure research, basic research. They like to call it Bohr research. It's like quantum mechanics, stuff like that. The pure applied research, when you're actually, you have the application in mind, the Edison, Thomas Edison quadrant. And there's this middle ground, the Pasteur quadrant, which is the use-inspired basic research. So we are doing basic research, but we have an use in mind. Okay? So that's the kind of research we are doing. So let me rephrase the goals again after this background to try to make it even more, a little bit more specific. So the aim is to develop user-friendly software to rationally guess the biological functions of genes from sugarcane. And what does this mean? What's besides the beautiful phrase, what's the actual materialization of this aim? We have to, in some probabilistic way, to define the probability of a gene X have the function A, for example, given some evidence. So that's why that's where the Microsoft expertise comes to play. So the idea is to make this annotation to guess the function of genes. When I say rationally guess, I'm saying to define, to estimate the probability of a given gene X has a function A given evidence. So this is pretty much modeling quantitative and qualitative uncertainty. That's the idea of this rationally guess. And model is to model this kind of uncertainty to answer that kind of probabilistic question. Because nowadays what people do is just, they simply put gene X has the function A and that's it. We want to do better than that. We want to do something probabilistic. And how we are going to do that? Well, in looking through the lenses of the information technology, we are going to create, we have two audiences here for this kind of project. There's the biologist. For them, we need to provide web portals. That's the IT part. Web portals, easy to navigate, easy to use, where they can find all the information that is relevant for them. But there's also the other guys, the guys who actually program. So for these people, for programmers, we intend to create some web services, which is not the same thing as web server. Web services to make this kind of tools we are going to develop available to everybody, not only in this community, bioenergy community, but in other communities too. And moreover, to achieve our goals, we are going to use something in the artificial intelligence, something that people in artificial intelligence community call machine learning. So this is the technique we are going to use, machine learning, to make this probabilistic annotation. From genomics, we are going to borrow the concepts of phylogenetic trees. So we are going to merge phylogenetic trees as a biological concept with tools from the machine learning subfields, and we are going to merge this using Bayesian networks, which is a well-known technique, a subfield in machine learning that has this ability to deal with uncertainty and quantify uncertainty. That's why here is the point where we had to cry for help. So it's here that the project, the bioenergy agenda, meets the Microsoft interest, and that's why this is why we decided to propose this joint project, because Microsoft research is well known all over the world on their Bayesian network capacities, and they are knowledgeable on this. So we decided that's the main technology, if I could say something like that. It's not a technology in a sense of code, but technology in the sense of people who know this kind of subject, and that's what we were looking here in Microsoft Research. So for those who are not familiar with Bayesian networks, it's a graphical model where you just, this is a classical wet grass example. So when you characterize your uncertainty about the world using Bayesian networks, you try to display the variables you think are important in a graphical way. And graphs means these balls and arrows, and each arrow means something like this depends on that. So this is conditionally dependent on the parents. The parents are the guys above. So, for example, if you Seattle, it is cloudy. What's the probability of being cloudy in Seattle? 0.99, something like that. If it's cloudy, you can start your sprinkler to wet your grass, or it might rain, so you don't have to start your sprinkling. And the result of these things is that the grass is wet. So given that it's cloudy, you can know the probability of this. You can infer the probability of the grass being wet, because it can happen because you used your sprinkler or because it rained. But what we want is not this. We want to invert this. We want to take the evidence of, you put your hand there and see the grass is wet. This is evidence. So now what's the probability of being cloud, or what's the probability of that rained, or that's why you're trying to make inferences on possible causal relationships that you model in this way. This is what Bayesian networks are. This is the classical wet grass example. Just to have an idea what's a Bayesian network. And what's the theme for this task? So we from the bioenergy side, we team up with Professor Glauser from Brazil, who is the leader of this BioN program. So she's the general coordinator. She's on board on this project. On the artificial intelligence side, there's David Heckman here from Microsoft, who is there, waving, and who is the leader of the eScience research group here in Microsoft Research, one of the leading experts in Bayesian networks and machine learning. These people got on board and to give the support for this project. And there's also my team in Brazil, which is I just got this position as a professor, so this is my first year as independent researcher, and this is the grant that was granted by FAPESP. Is the first by Microsoft Research, and FAPESP is the first grant my lab got. So it's going to build the whole infrastructure, not just for this project, but for the whole thing. So this is my team, and this is my guys there, my students. Of course, not all of them are going to work in this project, but they had some this project is the main project in the lab because there's some indirect consequences of being in this research problem. There's other things that can benefit from that. I will talk a little bit about that later. So the budget for this project, it's a 2-year project, started 4 months ago, and it's it's, the most important thing here, I think, is the idea how they set up this thing. So there's half of the grant comes from Microsoft Research, but the other half comes from the Brazilian government. So I think this is important because it shows that both sides had lot at stake here. So that's why they are financing half. And the expected results are, well, from the bioenergy community side, what we are going to deliver, we hope to deliver. The annotation or re-annotation, because some things are already annotated. Some, of course, we are not going to find functions for everything from de novo, from zero. There are some stuff that people already know, but we are going to re-annotate these things to confirm, for any reasons. There's lots of reasons why one wants to re-annotate something. So we are going to annotate and re-annotate the sugarcane genome, or whatever part of it which is available on 2012. So this project it's running in parallel with the genome sequencing. So we are not doing the genome sequence, they are doing, but this project is running in parallel. So we hope to deliver the annotation of whatever they have at hand when we finish this project in 2 years. Of course, the whole genome of sugarcane is not going to be complete in 2 years, because it's a difficult plant. It's a real scientific challenge, but we are going to deliver whatever is at hand at that moment. Another thing we plan to deliver is the sugarcane expressed genome. So there's the genome static, but there's also the expressed genome, which is dynamic, depends on each tissue you are analyzing. This was already published in 2002, and there's lots of room to find functions for the genes that they are already annotated, but they have unknown functions until now. So we plan to apply these machine learning techniques to see if we can assign functions to these gold mines that might be hidden somewhere there. And moreover, we will also annotate some cellulitic fungi genome. So you can't go from zero to the sugarcane in one pace. You have to build in baby steps your skills and your knowledge. So we decided to use some useful tests. So we are going to apply the methodology and the technology to small organisms, some fungi, maybe some pathogenic bacteria that infects sugarcane, to get a handle on the problem, know what's going on, to really master the technique and master and generate some results as a side effect, let's say. So they are useful sandboxes. We will start small and get bigger towards the sugarcane genome. But even if they are not the aim, they are useful sandboxes. This is from the side of bioenergy. From the side from the IT technology or artificial intelligence side, what we plan to deliver, first of all, human resources. There is not a lot of people in Brazil that actually master this kind of technique. So it's important to train people, to put students to work in this, to enlarge the bioinformatics community, the machine learning community. So this is one important result we intend to deliver. But from the scientific point of view, the most important thing is one system, one annotation tool that can do this in an automatic fashion and probabilistic. So it must have to analyze a whole genome, for example, and delivers in an automatic fashion the functions for at least most of the genes in a probabilistic way. And finally, one result that we expect to get is this technology transfer from bioenergy to other fields. And I don't know if you noticed, but I'm at a medical school, so even if we live in a sugarcane region, it's a medical school, so we want to make this kind of Robin Hood-like of approach. You know, the Microsoft project is going to found a specific thing, but this kind of capability to annotate genomes in a probabilistic fashion, this is useful for several other projects that are going on in the lab. So this Microsoft project is going to be indirectly funding this other research too. And this other research includes malaria, but not the malaria we are used to, the malaria that happens a lot in Africa. It's the other malaria caused by Plasmodium vivax, which is non-lethal. People don't die because of that. Maybe that's why there's no such attention in this kind of malaria, because you don't die. Oh well, you get very sick forever. It's not benign. It's really tough, but it's not as critical as the main African malaria caused by Plasmodium falciparum. So we are going to use this technology to annotate Plasmodium vivax genes too, and there's also what I call the biorubber, also known as natural rubber. There's in the Amazon there's a tree where you just make some cuts in the tree, and you got some kind of latex, and this is what people use to make natural rubber or biorubber, which is a renewable alternative for the petroleum-based rubber for several applications. There are some applications that require this kind of natural rubber. You cannot use petroleum-based. For example, some medical applications, some airplane tires, they have to be made of natural rubber and stuff like that. It's the same kind of project. There's a parallel project going on down there in Brazil to sequence the Avia brasiliensis, which is the name of this tree, for biotechnological reasons, which is going to end up in the same situation that the sugarcane plant. You will have a bunch of sequence, and you have to find some functions or assign functions for that. So this technology where we are trying to build here, it's something really general. There's the component, the applied component, which is bioenergy. We want to do something applied that's useful in our region, our country. But there's also the scientific problem, which is general and important, which is the probabilistic annotation. Okay? I think that with that, I end up my presentation. I hope everything is clear. If it's not, please, this is my email. Feel free to contact me later for any questions that you might have. Thank you.
Thank you, Ricardo. We have time for some questions before we go with the second speaker. So, any question? Okay. Can you say your name and your affiliation, please?
Sure. I'm Fabio Gonzalez from the National University of Colombia. Just to know exactly what you're doing, so you're analyzing the expression of the genes. A little bit. No. I mean, I would like to know some more detail about what exactly you are doing.
They're going to sequence the whole genome of sugarcane. If it's sugarcane, if it's the other applications there, you have the expressed genome, the transcriptome, if it's the other tree. But let's focus on sugarcane. They are doing their sugarcane genome. So we will have the whole genome sequenced. Now you have to assign functions to these genes. Otherwise, it's going to be just a soup of letters. So what we are going to do is to build a system that will take in sequence and assign gene ontology functions or terms to these sequences in a probabilistic way. Is it what you...
Yeah, but the thing is that you need data to train the...
Oh, that's... okay.
And the problem is that you don't have really examples of genes and function, or Or are you planning to use the information from other kind of plants or something like that? Or?
Yeah, that's I didn't put the scientific meat here. I just talked about the overview. But the idea is, you have suppose you have a sequence. You can build a phylogenetic tree. That's the concept we are going to borrow from genomics. You build this phylogenetic tree. Then you use the structure of the tree as the expert, let's say, in the Bayesian, in the machine learning community. One will call this the expert. So you build on top of this tree, this phylogenetic tree, the structure of the Bayesian network. So each node in the tree.
I think it's.
Each node in the tree becomes a node in the Bayesian network. Can you see? Then you just superimpose a Bayesian network on this phylogenetic tree. Then the information on the related sequences from other species are going to be propagated as evidence.
So you use information from other species?
Yeah.
Oh, okay.
That's okay. Otherwise, it's going. Okay. But when they are available. When they are not available, we are going to try different approaches. For example, transcriptome. They have some transcriptome data, because to create this Bayesian network with phylogenetic tree, you are implicitly assuming that you have neighbors to build this tree. If you find some gene that is really unique to a given organism, then it will be difficult to create this tree. Then you have to find other kinds of evidence. The good thing about this model we want to build is that it can incorporate all kinds of evidence that you can put there if you model them as probabilities.
Okay.
It's better.
Yeah. Clear.
Is there another question? I have one question.
Please.
At the beginning, you mentioned why sugarcane would be better than corn for getting into biofuels. Can you elaborate a little bit in terms of which one is more efficient and why?
The efficiency of sugarcane, it's much higher because there's a higher content of sugar per kilogram of mass or something like that. But this is the technical reason why one plant is better than the other. I think that we cannot forget the rest of the reasons, which is does not compete with food. I think that this is one important issue. What else? Does not require some input energy, because when you plant corn, you have to use the delta energy in the end. It's not so great when you use corn. When you use sugarcane, the delta energy is bigger, so it's more efficient in this way because you don't have to throw so much energy in a vague sense to make energy in the end when you use sugarcane. Are you okay? Do you want?
Yeah.
Is it okay?
Mm-hmm. Okay. Full name and affiliation.
My name is Guido Caicedo. I'm from Espol in Ecuador. I don't understand clearly why sugar. I mean, you mean that this doesn't compete with food in the sense that I think there are countries that export sugar, and I mean, it's out of a sugar cane. So, I mean, there could be a company that wants to, export sugar and to provide to other country, but then there's this biofuel thing. So, I mean, how is it's not competing? In which I don't have the scale or the dimension of it in order to understand why it's not competing with food.
When we say that it does not compete with food, is in the way it's in a sense of course. People do sugar with sugar cane, of course, but the amount necessary the market for sugar is not going to be too impacted by the ethanol production. If we hope so, we imagine this. Of course, if the biofuel production gets much more lucrative than sugar, then it's clear that people will use sugarcane to produce bioethanol and not so much sugar. But there are other options to produce sugar that are not only from sugarcane. In this sense, we say that doesn't compete. Of course, this does not compete with food. It's an approximation, of course. Of course, if I was a guy planting sugarcane and bioethanol is giving much more than sugar, of course I will switch. But the thing is that the system is set up in a way that generally people don't sell sugar to create sugarcane. It's not like you don't harvest your sugarcane, makes into sugar, then there's another player in the market that buys the sugar to convert in bioethanol, you know? It's generally it's the same guy that does almost everything, not everything from planting, but it's not so. Can you see what I'm trying to say? So you don't diverge that much because it's all you. There's no difference between the sugarcane that makes sugar and bioethanol, but the whole system, the industrial system, it's set up in a way that generally people do one thing or the other thing depending on market, of course. So what I'm saying that does not compete with food, it's an approximation, of course. But there's other sources to get sugar. You see?
Thank you. Anyone with a question? Okay. Thank you very much, Ricardo. Let's continue with the second speaker of this afternoon. The second speaker is Dr. Celso Bonrando. He's a researcher at the Center for Earth System Science in the Brazilian Institute for Space Research, INPE. The title of his talk is Network of Environmental Sensors in Tropical Rainforests. This is another project funded by the Microsoft Research FAPESP Virtual Research Institute. And this specific project involves the participation of, it's a partnership among Microsoft Research, Johns Hopkins University, University of Sao Paulo, and the Brazilian Institute for Space Research, INPE. This talk will describe the research activities to be developed to test the use of prototypes of environmental sensors in the Amazonian rainforest in Brazil, along with the development of software tools for data quality control and integration. So please join me welcoming Dr. Celso Bonrando.
Okay, thank you very much for the invitation, Jaime, and it's a pleasure to be here. I'm going to talk about this project that's very exciting for me as well. I'm also it's also my first project that I'm coordinating as a researcher at INPE, and this is actually started from a previous project or an initial project that Microsoft Research initiated together with INPE and the University of Sao Paulo and Johns Hopkins University to perform a pilot study. And now with this call from FAPESP, we put up a new project to further develop these or to address some issues some of the questions that we already got from the previous project. Just as a motivation, I'd like to start by saying what is the motivation that we have at the Center for Earth System Science, INPE, into researching the tropical forests, or in general the whole biosphere as well. This is a slide that shows illustrates some services or the influence of forests in the climate system, and actually it also illustrates some of the main uncertainties that we have that related to forests in the climate system, and the arrows there indicate some effects that forests do in the climate. Like there's the issue of carbon storage. Forests take up carbon from the atmosphere, and this influences a lot the climate system, and actually these effects can dampen the anthropogenic emissions by absorbing part of the carbon or the greenhouse gases that are being emitted, and this is a very important service, and actually it's part of the biggest, it's one of the biggest uncertainties is still in climate models. How will that happen in the future, and how does that? How can we better understand all these processes and put all this knowledge into our climate models? Well, this is just a brief outline of this talk. I'm just show a little bit about the environmental issues that we focus, the biosphere-atmosphere interactions, and some of the technical and scientific challenges that we are facing in this project or in this type of research. For example, the environmental conditions in the tropics, or well, the idea is to develop new sensors or to test an integrated system that will work in the tropics, and there are a lot of technical challenges for that. And the heterogeneity of forests, this is more of a scientific challenge or a scientific question that we want to address, and for the development of the integrated systems. And I'm going to show a few results from the pilot study that was performed last year in the Atlantic coastal forest, and some of the future plans. And our future plans are actually part of the future plans, which are already being addressed in this current project, that we will test and deploy and expand the network of sensors in Amazonia. So a little bit of the biosphere climate interactions. How does that happen? How the biosphere influences climate, and the main driver for climate, and it's the sun, the energy, solar energy that comes from, we say from the atmosphere, actually from the sun, but it's an external force that we use. Part of this energy is reflected by the biosphere, by the surface, and there is also part of the energy is absorbed, and the surface itself emits some of this radiation, or we call it terrestrial radiation. Also, there's energy that comes from the atmosphere itself, that the atmospheric radiation facing down. So all this energy that stays in the biosphere is used it uses to heat the surface, and this energy is transferred from the surface to the atmosphere, and also used in the evaporation process. So it also influences the whole water balance as well. Of course, the evaporation to the atmosphere, and part of this water, most of this, falls down again as precipitation or as rainfall. So these are key features of the interactions between the surface and the atmosphere. There's also CO2 now carbon. How does that influences the exchange of carbon and by assimilation of forests and also by respiration? This is also an really important feature that we want to understand, we want to measure and model as accurate as possible. And also some important things in climate interactions are the exchange of trace gases and aerosols. So how do we measure these things? One of the most important techniques is to actually go to the field to build a tower in a forest, ideally a uniform forest, and put up on top of these towers sensors that measure the exchange. So actually there are a whole worldwide network of these towers, and these are at the locations of the tower. There are more than 400 now in the whole world. And this is just an illustration of the measurements. Like all these exchange happens because of the turbulence. The air is moving over the forest and carrying part of the energy up and down. And when we put up a tower there, we want to measure across the forest surface to add up whatever energy or carbon is going up and down, and we add up everything to get the full exchange of these. The challenge there is that when we put one tower, actually when we measure one thing, we can relatively well measure. If we have a flat surface and uniform terrain, we can add up everything very well that goes up and down. But the problem there is that the sites that we are measuring, these are almost always much more complex than just a uniform terrain. At some level, these sites are always, the natural surfaces are always complex. This is an illustration, a terrain map of the region in Amazonia that we are actually going to measure later. We are going to further study in this project. It's never a flat surface. There are hills and valleys there. It is all covered by forest. So when we see that picture, this picture that we see, it looks like just a very uniform terrain and just like a big green sea, but it's quite complex. And the challenge here is that when we put a tower, this is an illustration for the most important challenge that we have in measuring these fluxes, particularly the carbon fluxes, is that when we put a tower, it's usually put on top of hills. It's really difficult to measure in the valleys, but well, this tower it actually has what we call a footprint, or there's a region that it can cover. Let's say it can see this region of the surface, and then this illustrates if an air parcel near the ground is enriched with CO2 during nighttime, like where there's a lot of microbial activities and emitting CO2 inside the forest, and this enriches the air parcel. But since we are dealing with calm conditions, these parcels they go downhill, they flow downhill with little exchange on top of the forest. So we hope that when we add up everything in the whole day or the next morning, we would all those parcels, they would go up in our sensors as well. And then when we add up everything, we got completely covered the exchange. But in reality is that in next morning when starts the turbulent activity again, these parcels, they go up, but part of the parcels which are illustrated like in yellow there, they go up outside of our view in the tower. So the CO2 emitted next morning, it goes outside of our view. So we are missing part of this carbon, or part of this exchange. These are measurements that actually show that this is a CO2 concentration along the topography there, and we see actually that there's a flow. You see that there's a buildup of carbon there, CO2 concentrations there. This is the yellow and red colors are more enriched with CO2, and it looks like a river of CO2 in the valleys there. And actually, this is a picture of just in the morning. You can see, in the valleys, it forms also a very stable layer of fog. This is frequent there, and it looks like there's a river of, that is formed in this area. And this is a picture taken from the tower itself. Another challenge that we are trying to cope here is the heterogeneity of the forest. This is a satellite image. This is how climate research used to see the Amazon forest until 10 years ago. This is how we used to see it. Actually, this is a mask used in most models now, a mask of the river and the terrain, the surface land. But however, when we look at a more detailed image of terrain, we see that it's hardly never flat or never really uniform. And actually, there's a new classification tool that we are using at INPE based on the terrain, based on a lot of information of the terrain, that we come up with this classification. So we have different classes of the terrain now. And this picture shows that it's really very much more heterogeneous than we were dealing with before. So,
what are those classes?
So these are classes for a tool that's called HAND. It's I'm sorry, I should have shown it. They're just classes of low land, slope, high land, and the 2 degrees of slope there. So, the challenge, how to understand, how to deal with this forest microclimate. Well, for heterogeneity pose big challenge to our understanding of the whole system. Actually, we need an approach that recognizes the complexity of the variability, of the spatial variability of these variables. So we need to develop new systems that ideally would be able to measure within and above the forest with high spatial and also high temporal resolutions. Of course, some technical challenges that the environmental conditions are very also challenging. There are high insulations and high humidity that can damage the sensors a little with a higher the life expectancy of these sensors are usually lower in those conditions. And also, well, some areas are very inaccessible, and there are issues with bugs and rodents and all sorts of challenges there. But we also need to make in this system, we also need a good data quality assessment, and hopefully very nice visualization tools as well as a nice thing to provide to the users. So, well, I'm going to show some of these results that from this pilot study that were performed last year in a different site in the Atlantic coast of Brazil. In this study, we built up a network above the forest with 6 towers and connected by cables, and put up a number of sensors in building a grid above this forest. So this is an illustration of the network of sensors, and I'm going to show some of the measurements here. So these are just an example of the spatial variability measured at about 25 meters above the ground. And you see that, well, it shows a nice daytime variation and a number of sensors, and they all measure similar variations, but there's also quite a large spread of temperature or of conditions, which it's related to the spatial variability of this region. So here it's an example of two different sensors, and you see that there's the spread of the temporal variation, so a variation on several days, and you see that there are some conditions that, like, there was a drop of temperature here. It's probably caused by some frontal system that dropped the temperatures there. But it's interesting to see that all the sensors respond quite well. So as a test for this system, it looks like it's working pretty good for this type of research. Here's another example that we can see with this data set. We can look into different conditions, and also we can look into the profile of temperature within the forest along the day. So it's a very nice, interesting to see see that during daytime. Here's during daytime, and you see that there's a warm region in the forest. Actually, at this time, at this hour, you see that the top of the forest is the region where there's which is heated the most. And this sort of measurements are very interesting to understand how the microclimate within the forest is going on, and how is that influencing those exchanges that we want to understand. Another visualization that we could do with this system is I'm going to show here a few slides that will show the spatial variability of these sensors. And what we are showing here is the deviation from a minimum temperature during the day. So we were saying that from the minimum temperature as 0, and then we will see how how much this varies from the minimum temperature. And here's how it goes along the day. We see that the time is moving an hour every time here. Then we getting into daytime, and we see that it's heating up. The whole forest is heating up, but the nice feature here is to see the spatial variations as well. We see some spots, warmer or cooler spots in this region, and this is actually a very innovative aspect of this network. It's very hard to measure at this scale this type of thing. We cannot measure. We usually have models to analyze this thing, but to have a system that can actually measure this and actually validate these models is pretty important. And so as a results from this pilot study, which is it showed that there's very good physically sounding data that came up from this system, and there's also detection of improvements. That this pilot study was also very important to test this type of system. There's actually we saw that there's room for improvement. For example, in the humidity measurements, they are not shown here, but there are some issues that of humidity with the humidity sensors, and this is actually a nice thing that we are now in this project working on new humidity sensors, and from this now we are foreseeing to bring this system up to Amazonia. It's also again there's this challenge that it's a wild environment, and pretty difficult to access sometimes, but we are confident that it will be a very nice project. So there are the two supportive projects that are listed here. One is this project that I'm leading now in this call, but there's also a project from Humberto Rocha at the University of São Paulo that it's more a regional integration to study the carbon flux, this carbon exchange in Amazonia. So this is just a slide to highlight the future plans or the current and future efforts that we are working in this project. Again, this project is built on sort of three different pillars. One is the assembly of new sensors, or actually in this part we are mostly using a lot of the expertise that we got already from this previous project, but focusing now on new humidity elements. So there will be there's an engineer, a materials engineer working on a new element for humidity. Software infrastructure will also be adapted, and new features from the previous project will be developed at INPE, and the application is, of course, the part where I'm more interested as an environmental scientist. How do we address these questions using this system? What sort of questions we can answer from these systems, like how to get the variability of temperature well into the models, to reduce uncertainties that are associated with this variability. This is a slide for about the the infrastructure that are being developed or further developed based on previous knowledge, on previous tools that we have. We have, of course, the issues that the data entry from the sensor network and the database that will be built in this project. Part of these tools are already available or are already developed from previous projects, like the ability to do simple reports and visualization of this data, some spatial and temporal analysis of data. But now we want to further develop these tools as web services to provide access to the data. We have lots of other environmental databases at INPE, which we can integrate these tools. We integrate these other databases within these tools, and create some virtual laboratories as well. So it's of course this system can be a pilot for other environmental databases as well at INPE. Just to give you an overview of what we are planning within the Amazonia now in this project. We do have 2 towers built already in this terrain. This is an illustration of the terrain there. We do already have 2 towers, so we will deploy sensors along these towers. We got a vertical profile of this. We will build a new tower also in the valley, forming a triangle, and we hang cables from the trees so we can put the sensors on a triangular sort of 3-dimensional network, and we can just spread the sensors around these towers and have a more detailed measurement of the spatial variability of temperature and humidity. And from these measurements, we want to study the variations of density, air density, and try to infer how is the carbon flowing downhill as we are hypothesizing here. So it's a partnership. These are from these institutions, as Jaime already mentioned. And I will show you a video of, as we do have we still have time. I'm going to show you a video of the project, which is.
Brazil still uses very little of its potential in terms of natural resources, in terms of renewable energies. So all this potential is up for exploration, and the exploration really starts with science.
It is very important for mankind to understand the environment so that we can live in a situation in which life and development are sustainable. And if you want to have sustainability, you have to understand how the environment works, how things are connected, so that you don't create situations in which you are going to make permanent damage to the environment. Most countries in the world have already destroyed all the native forests they had. Brazil did not.
Initial concept of these experiments: how can we monitor a large area of forests that would provide us with a 3-dimensional view of the tropical forest of the Amazon functioning? From the outset of this project, we believed firmly that it should be done through international collaboration. So we bring the best of all the groups involved. Johns Hopkins with experience in already deploying inexpensive sensor networks in tropical forests. Our expertise in running these experiments for 20 years in the Amazon, and of course Microsoft Research providing the means and the software development.
It's extremely enjoyable to be able to take a new technology that we're adopting from our collaborators at Johns Hopkins University and bring that down to other researchers who are operating in Brazil. Through the process of that adaptation, create a new scientific data set and create a whole new methodology which can be applied again and again to other research projects.
We employ two types of sensors. A thermometer, which measures temperature, and a hygrometer, which measures water vapor concentration. And a third one, solar incoming radiation sensor, or a radiometer. We designed a network of towers over a hill slope in the rainforest and attempt to measure that every minute.
So there's one central tower, and around that are 5 others total. And then radiating out between the central one and all those towers are cables. And then between the perimeter towers are cables. So that's the arrangement. And what we did was we took our sensor network and we went out there and we deployed that up into both on top of the towers and along the cables. So we created a mesh above the forest canopy. In addition to that, we also placed sensors on the towers below, so inside the forest canopy, and then we made a transect of about 12 of these sensor network nodes that went up the hill along the ground. They're about 1 meter off the ground. Challenge number one is just to make the stuff survivable in the rainforest. Once you've managed to solve the problem of not letting the water get at this stuff, is to actually have the thing operate for that period of time without running out of batteries. So that's something that the Johns Hopkins team have been working very hard on, and the strategy that they use is called duty cycling. The next thing you do is you make sure that you have radio connectivity, because the radio link is how you get your data back. And then finally what you want to be able to do is you want to have a robust data recovery system, and then you take that laptop out and you connect it to the internet and you push that data through the internet up to Johns Hopkins University in Baltimore, Maryland, where it gets ingested into a database and it gets processed to where it can finally be used for scientific analysis. We had a deployment time period of about a month, and we had a total of about 200 sensors, and they're taking data once every 30 seconds. And so that represents a potential total data yield. And I would have been delighted if we'd gotten up to something like 70% of that total data yield in the camp. But actually what we wound up getting was about 98%. So we did extremely well against our goal. If we can successfully carry out this pilot study experiment, then we can go ahead and scale up the experiment, perhaps by a factor of 10. So we take not 200, but 2,000 sensors. We take them into a larger area. Maybe it's instead of on the Atlantic coast, the rainforest there, we go into Amazonia and do work there. So there's all kinds of expansion possibilities.
So always I've been very concerned how science can help to achieve sustainable development in the Amazon.
Climate change is a real thing, and it's not just the increasing temperature, but also the implications for variability in weather. Well, if we're going to understand that and how that couples to how we use our resource, then you need to understand the system better. It's a really complicated system. The general proposition is we're taking steps to better understand a very complicated system so that we understand the implications of our choices.
Right. With that, I close the presentation. Thank you.
Thank you, Celso. We have still 5 minutes for questions. We also have Rob Fatland here, who is our program manager. You just saw him at the movie. He was very much involved in the pilot study in Brazil.
Hi, this is Bob Davidson with Microsoft. I've done process control before Microsoft with sensors all over the place, and having multiple sensors and keeping them calibrated together has been very hard in a factory situation. In this situation, it looks like it would be close to impossible. What sort of things are you doing with your data quality to make sure that when you have one sensor reading 20 degrees and another sensor reading 22 degrees, that it is actually 20 and 22 degrees, as opposed to having drift or other things happen to them?
Well, yeah, we do have the sensor elements are relatively small, and we do have a lab at INPE that we put them all in this chamber, but that we do. So for this project, we are still able to calibrate them all together prior to deploying them in the field. Of course, it is, if we want to increase the number of sensors, it's a very challenging thing that we are unable to calibrate them all if we want to go to thousands of sensors. But well, what we are trying to do is to have them as better as possible calibrated. So, but yeah, indeed, it's a challenging thing when that we need to think further in the future how to deal with that in the future. For this project, we are still managing to do that.
So you're doing it basically by using a precision standard.
Yes.
And presuming that you're not going to drift in the field, so that the data you're getting back is reliable data based on.
Yes. Well, what we are planning now, with this, we do have a precision standard, and we do it. We do a calibration prior and then after the deployment in the field. So we bring them back to the lab and we do a new calibration to test that.
So,
yeah, I would like Rob.
I just wanted to add one other thing to that also, which is that
The microphone.
Can you hear me through the sound? It's tricky. Okay, sorry. So just to further address this with the pilot study where we were out there, we co-located sensors so that if they were perfectly calibrated and solid all the way through, then they would agree with each other, down to 2 or 3 decimal points, which they don't. So as the day heats up, one of them will heat up more than 2 centimeters away from it. And so that's part of what we're trying to do with the engineering here, is to characterize the way that kind of thing happens, because you have these microscopic centimeter scale variations in the environment itself. And you're right, the bottom line is when I measure 20 degrees, when that's the number that comes out of the process, what was the temperature in that area? What does that mean? It's really, really hard. Somebody once said, if you want to drive yourself crazy, try and measure the temperature of a bucket of water. So it's an ongoing process, and it's not something we're minimizing at all. So.
Yeah.
Thank you, Rob. Thank you, Bob. Any other question? Okay, Michael.
Okay. Michael Smith, University of Trinidad. You had mentioned, or both of you had mentioned, that you would have been happy with 70% data recovery. You got about 98%. What were some of the factors that you thought would affect your data recovery that you didn't experience, that you think you may see as you start to expand this to more nodes and more networks? And what was the 2% part?
Well, maybe I hope Rob can take that.
That's probably for me. So actually, it ended up being 99%. And part of the challenge here is that you have these very simple computers that are up in the environment, and they're communicating wirelessly through telemetry. So if they fail, and they all survived, so that was a big part of why we were that successful. But if they fail, they drop out for periods of time, then they'll sort of develop amnesia, and you won't be able to get that data back. And in anticipating the future work, if we were to take that sensor network, which was 50 network nodes, and scale it up to 500 or so, now the amount of interconnectivity of that wireless telemetry network increases in complexity, like the square of the number of nodes. And so that you end up with this possibility of data traffic jams. And if the more your data gets jammed up in transit, the more time you spend trying to pull it down, and the more locked up you get, just like a traffic jam. So that's part of the technical challenge. And that's why working with Johns Hopkins has been so much to our advantage, because they've been working on this for a long time, for years now.
Thank you, Rob. I think the time is up. So thank you again to Celso, thank you again to Ricardo, and thank you to you for attending the session.